So from now on we'll look at some circuit design, we'll start and then we'll continue from next class. So yeah, let's start with the first operation, which is sampling. So from now on all circuits. Okay. So as usual, I mean sampling is simple. You just need a switch that opens or closes. This is my Vin, and I have to store the sample voltage. What do I use? Capacitor like this. This is Vout, and the control for the switch is like this. We'll call it phi. So phi does this. So we'll assume that this is an ideal switch, which means when the switch is closed, it is a perfect short. When the switch is open, it is a perfect open. Fine. Let us say now my input is like this, something. So let me also mark the points here. Yeah. So now tell me, when the clock is high, the switch closes. So what will be Vout? Vout will be equal to Vin. So if I sketch Vout in yellow, it will be this. At this point, the switch is open. What will happen to Vout? There is no path for the capacitor to discharge. It's going to retain the voltage. Again, when the switch is closed, it will be Vin. Switch is open, voltage is held. Right? It's a simple capacitive circuit. So as you see, this circuit kind of operates in two modes or two phases. In first phase, it is exactly tracking the input. In the second phase, it is holding the input. Yes, this is called as track and hold. Is that okay? So now can you look at this circuit and look at this waveform and tell me at what time instance the signal is actually getting sampled. Let us say look at first clock period. At what timing instant the signal is actually getting sampled? And the clock is exactly falling, right? At this point is when it is sampling and holding. So the falling edge defines the sampling instant. So let us say we'll define this as t equal to 0. This is the next sampling edge, Ts. This is all our convention. You can choose anything. Cool. So this is the basic sampling circuit. So it just contains a capacitor and a switch. The capacitor is a nice capacitor, nothing to know new. The only thing is a switch. How do you make a switch or implement a switch? Transistor. In fact, it is the quest for making a switch led to the invention of transistor, and that is what is driving people ahead. So we'll deal with MOS. So the simplest switch we will use is a MOSFET like this, right? But as you know, a MOSFET is far from an ideal switch, right? So what is the first non-ideality you can think of? Simple, right? As of now, we know the switch is like this. It is supposed to be a pure short circuit when it is closed, open when it is open. When I use a MOS switch, it's, of course, it's clear that it is not a short circuit. So there is going to be some on resistance when the switch is on. So that's what we'll first look at, the finite on resistance. So first what we'll do is this. We'll look at what happens when we have a finite on resistance with the switch. What is the effect it has? Then we'll see what is the on resistance for a transistor, and then based on those two discussions, we'll see how we can, choose a MOSFET. So one thing is, once you sample the signal, obviously you can go and directly quantize it, or as we'll see going forward, we'll do a lot of processing and then do quantization. Okay. So the point I want to drive is, typically in circuits, a switch can see two kinds of inputs. One, when it directly is looking at the continuous time signal, it sees a continuous time input, and let us say you sample it and then you are doing some more processing on this. and then the processed data is sampled. Remember, once I sample it, the signal is kind of held like this, right? So the succeeding stages or the switches used in the succeeding stages will not see a varying input, it will see a held constant input. Okay. So we can have two cases. One is when the input is time varying, one is when the input is a constant. Okay. So let's look at both cases. Let's start with the constant case because that is easier. So let's look at a case where the input is constant, so I'll model it as a DC voltage. Okay. So I have a switch, and to model the on resistance, I'll include a resistor in series with this fellow and do this. Let us say this is R on and C.
So let's use a constant input for some specific period.
Correct. When this, yeah, if you see the output of the track and hold was like this, right? Now the second stage where to process this, it should be processing this data. Correct? So it will be seeing the portion where the input is held. That's okay? Yeah, you are right. It is not like it is always constant. In track phase it is tracking, but the second stage will not be interested during this part. It will be interested in the samples. So after sampling, which is this point, the signal is constant. So here, this is a simple circuit. So let us say the switch is now closed. So let's say I define this as t equal to 0, I mean for simplicity. So tell me what is V out. Should be knowing this now, hopefully. What is V out of t? I mean, this is function of time. So what this is? Okay. Okay, I mean, this is a first order circuit. To exactly write its time domain expression, what are the information you need? Initial voltage, final voltage, time constant. Initial voltage is what? Assume the capacitor is uncharged, 0. Final voltage is V0. So again, hopefully this is not very alien. Okay. This is what we'll have, and let me mark the clock phases. Let's say this I called as t equal to 0. This is one clock period Ts. So we are stopping the switch at this point, which is Ts by 2. Right? So the switch is closed for a duration of Ts by 2. Is that okay? So I'm interested in the voltage sampled when the switch exactly opens. So I'll be looking at V out at what time instant? Ts by 2. Is that clear? So this is simple. It's going to be V in 0, which is the value you want, minus V in 0 e power minus Ts by 2 R on C. So how should I choose my R on now? I mean, what do I want this voltage to be ideally equal to? V in 0. You want this term to go to 0. What do you do for that? Yeah, this fellow must be much greater than 1. So R on times C is the same thing. If the RC time constant is very small, it's going to charge fast. Limiting case is when R on is 0, it just jumps up instantly. Okay. Cool. So this is simple. Now let's look at what happens when the signal is time varying. So which means I'll take a sinusoidal signal, because any signal you can think of as sinusoids. Oops. So this is, let us say, some cos of omega naught t. Again the same thing. I have R, C, capacitor is uncharged. I am closing at t equal to 0. So what will be the output here? High pass filter. This is not high pass, but V out of t. But how will V out of t look like? No, you are again going in frequency domain. I am asking time domain. It's not integration. Yeah, okay. At least in steady state, how will the output look like? Yeah. See, what is the frequency response of this h of j omega? This is V out. V in. What is the frequency response from V out to V in? V in V2, yeah, it is 1 by j omega c by r plus 1 by j omega c. Fine. This is 1 by 1 plus j omega r c, which means this is a filter which has this transfer function. I feed in a sinusoid at a frequency omega naught. So the sinusoid will be scaled by this transfer function. The magnitude will be scaled by the magnitude of this fellow, and you'll have a phase shift, which is the phase at that frequency. So in steady state, this is what you get. It will be 1 by amplitude will be this, right? It's r on square c square. I think I made a mistake, but it's okay. And then you'll have cos omega naught t. What is the phase? Tan inverse of omega naught rc. Okay. This is what you get in steady state, but remember, it won't jump to this instantly. There will be some transient. You work out properly, and you think the transient will stay, it will decay, or it will increase. It has to decay, and there is only one time constant here. It will look something like this. The transient I have not written fully, you can work out. Then do this. So here again, if I choose, or I will say I am interested in the V out value at t equal to Ts by 2. So I look at, right? I want the transient portion to die down soon. So which means I will choose the same thing. Ts by 2 must be much greater than r on time c. That will make sure that this fellow goes to 0. Fine. But we also have this thing, right? So here, ideally, what do I want this green term to be? You just want amplitude to be 1 and cos omega naught t at Ts by 2. This is what you want. So which means, how should I choose? What should I choose here? Which should be less than, what should be less? Omega naught r on c should be fine. So I ensure that the phase is 0, approximately 0, magnitude is approximately 1. So this imposes another condition. R on time c must be much smaller than 1 by omega naught. From the static case, you got r on c to be much smaller than Ts by 2. So yeah, you can choose whichever is the stricter case and kind of do. And typically this will be the most stricter case, because you know you are talking about 1 by 2 fs, correct? And this is basically the input frequency. Input frequency will be smaller than fs, so this most likely will be the stricter condition. Okay, so this is how you have to choose. So now let's quickly look at a MOSFET and then we'll wrap up. So let's look at an nMOS. So I'm sure everyone knows transistor, at least the IV relation. So this is a simple MOS switch. V in, V out. To turn the switch off, what should I do to the gate? Off. What should the clock be equal to? It should be 0 volts. If it is 0 volts, in which operating region the transistor is operating? So I'm sure people have taken 610. The operating regions are covered. This is done. So when it is on, to turn it on, what should I apply at the gate? You apply the maximum voltage you have, which typically is the supply. And let us say the switch is on and it's working reasonably well. What can you say about V out then, approximately? No, the switch is on. If the switch is on, it is working reasonably well. V out is equal to what? V in. This is supposed to be a switch. For God's sake, it should pass V in to V out. That's all. So this should be approximately V in. That's what you want. So what is the drain to source voltage now? Drain to source voltage is this. This is 0. So what is the operating region now? And I'm sure you guys know the current relation. ID is blah blah blah. I'll write it. It's not critical. It is VGS minus VTH times VDS minus VDS square by 2, right? And here VDS is approximately 0, so I'll ignore the last term. Okay. So when the switch is on, what can you say about VGS? Can you tell me what is VGS when the switch is on? Approximately? Yeah, but the value exactly is greater than VDD. VDD is gate. What is source? Fine. So let's put it here. This will be nMOS W by L, VDD minus Vin minus VTH times VDS. So we have to, let's say you want to find the on resistance of the switch. You take the derivative of this with respect to VDS. So the on conductance will be what? Yeah, this is the derivative. It's a linear thing, so it's just nMOS W by L, VDD minus Pin minus VTH. Okay. So now if I quickly sketch the on resistance, let me take it to next page. So my on resistance is inverse of this, right? If I sketch my on resistance as a function of input, how will it look like? For let us say Vin equal to 0, it's going to be some number. As I keep increasing Vin, what happens? R1 increases or decreases? I mean, if I keep increasing this fellow, the fraction here, I mean, this term reduces, so the fraction increases. And as Vin approaches VDD minus VTH, yeah, it tangentially goes here. So now we can clearly see, if I were to use an nMOS transistor as a switch, I cannot use it for this range of voltages. I can only use for a small range of voltages. Okay. So this is a good switch for low Vin. And other thing to notice, let us say the Vin is also low. If my Vin is changing in this small region, I mean Vin is changing in this small region, what can you say about R1? No, I mean don't look from the plot. My plotting skills are not great. Okay. So from the expression, if I change Vin, Vin is very small, but if Vin increases, do you think R1 changes or doesn't change? Changes. And R1, do you think it's a linear function of the input or a non-linear function of the input? So it's a non-linear function of the input. And this is pretty bad because let us say I restrict my input to be in this range, but my input is a time varying signal used directly at the sampling side. Now you saw that if I have a time varying signal, the expression I have is this. My Vout depends on R on here and R on here. My R on is a non-linear function of the input. So my output, do you think it will be a linear function of the input or a non-linear function of the input? Is that okay? Output will also be a non-linear function of the input, provided you make sure this to be much smaller than 1, then you can ignore it. If you can't ignore it so much, then because of the fact that we have R on here and R on itself is a non-linear function of the input, the output will be a non-linear function of the input. Okay, so this will be this is a non-linear function. So when you use it with a time varying signal, you will end up with non-linearity. Okay. So the conclusion is, if you have an nMOS, it is a good switch as long as it is a held or a constant signal, but for a lower range of input. How low is it? That is, you can decide. But even if the input is low, if it is time varying, only if you can guarantee this omega naught R on C to be much smaller than 1, If you can't ensure this, then you will have non-linearity at the output. Okay. So I'll stop here and we'll resume later.